In this video, I'd like to continue talking about finding the distance between two complex numbers. And specifically, I'd like to focus on finding a formula to find the distance between any two complex numbers on this complex plane. So to find this formula, we can start by plotting both of these numbers, and we can plot them anywhere we want. So let's say z1 is maybe right here. And we can plot z2, let's say down here. And to find the distance between these numbers, we can start by drawing a line between them. And ultimately, we just need to figure out the length of this line. And we can call this line d for distance. And the general strategy is to decompose this into a right triangle. So we can drop a vertical line here and connect that to a horizontal line going to point Z2. So the vertical line starts with an imaginary value. Let me label these. This would have an imaginary part of B1 and a real part of A1. And for Z2, this would have a real part of A2 and an imaginary part of B2. So when decomposing this into a right triangle, the vertical line starts at the imaginary part of Z1 and goes down to the imaginary part of Z2. And then the horizontal line, which will be perpendicular to this vertical component and parallel to the real axes, will start at a real part of A1 and go over to a real part of A2. And we now have a right triangle. These are perpendicular lines. And since we have a right triangle, if we can determine the lengths of these two components, the legs of the triangle, then we can use the Pythagorean theorem to find this distance d. So let's start by first making just a little bit of room. And we can focus on figuring out the lengths of these components, the legs of the triangle. So let's start with the vertical component. And the general strategy is that we just need to find the difference between the imaginary parts. But it's better to find the absolute value of the difference between them, since that way it doesn't matter which one we start with when going through the subtraction. So we can find the absolute value of b1 minus b2, or we can find the absolute value of b2 minus b1. And in both cases, we will get a positive answer, which will give us the length of this line. Now, there is another way to write this. We can also say that we're finding the absolute value of the difference between the imaginary parts of both z1 and z2. And we can write this either as z1 minus z2, or we can reverse that. We can say z2 minus z1. But the main idea is that we're finding the difference between the imaginary parts of these complex numbers. So the imaginary part of z1 we know is b1, and likewise for z2 it is b2, whatever those numbers actually are. So these are just different ways to write the same thing. In each of these cases, we're finding the length of this line here. And we'll follow a similar procedure for the horizontal component. And for this, we just need to find the difference between the real parts. Or more precisely, we need to find the absolute value of the difference of the real parts. And that way, by using the absolute value, it doesn't matter which one we subtract from which. We can do a1 minus a2, or we can reverse that and do the absolute value of the difference between a2 minus a1. And in both cases, we will get a positive length. And just like the vertical component, we can rewrite this as the absolute value of the real parts, or I should say the difference between the real parts of the two complex numbers, z1 minus z2, though again, we can reverse this order if we want, where the real part of z1 is a1 and the real part of z2 is a2. So now that we know the lengths of these lines, we can use the Pythagorean theorem. Since we know that in a right triangle, when the legs are a and b, we have that a squared plus b squared is equal to c squared, where c is the hypotenuse. So we can call either of these a or b, it doesn't really matter, just as long as the hypotenuse is d. So let's write all of this in. We can say a is the real part. So we can do the absolute value of a1 minus a2, and we have to square that. And again, we can write this with the other notation if we want. And then we will add that to the absolute value of the difference between the imaginary parts. We can do b1 minus b2, and we'll square that. And all of this is equal to the hypotenuse squared, and the hypotenuse is d, so this is equal to d squared. And lastly, to actually solve for d, we will take a square root of each side of this equation. So we get that the square root of the absolute value of a1 minus a2 squared plus the absolute value of b1 minus b2 squared. All of this is equal to that distance d. And the main reason to find this formula, to find the distance between any two complex numbers, is so that we don't have to draw a picture and draw this right triangle every time we want to find this distance. With this formula, we can just figure out what the real parts of each of the numbers are, figure out the imaginary parts, plug them into the formula, and we can find this distance d. And keep in mind that we could use the other notation where we write this using the imaginary or real parts. And we can also switch the order of these if we want. And since we have the absolute value, it doesn't matter if we switch this order, we will still get the same lengths in both of these cases. So let me just make a little bit more room. And it's important to see the formula in its other form using these real and imaginary parts. So let me quickly write that in. But the main idea with both of these formulas is that you can use either of them as long as you're finding the difference between the real parts, squaring that, and adding that to the difference between the imaginary parts squared. And once you take a square root of everything, you will get the distance between these two complex numbers. But ultimately, all of this is just an application of the Pythagorean theorem. So in the next video, we will look at an example where we have two complex numbers, and we will use this distance formula to find the distance between those two complex numbers.